Hello, welcome to class today. So, just two things to go through today: the warm up, which we'll go through, and then there's another assignment, two questions we're going to work through. Like last class, just work through with me. Warm up, I do want you to write the question out and sketch the graph and everything. The two classwork questions, you don't need to write everything out, but those should be helpful for the upcoming test. So it looks like your test will be on Tuesday at the moment, with everything just stays the same. So next Tuesday you'll have the test over this. I will still log in at 10 o'clock to go through something because there's parts of the test that might be confusing how I've kind of set it up. So still expect me to show up Tuesday at 10 to talk about the test. Um, I can't really limit your time on the test because just how things are. I don't know what your internet situation is or your device situation or anything like that. So, yeah. Um, you have your review on the College Board website. Make sure you work on your review on the College Board website. It does look like you do have to submit it. I thought I could go in and submit it for you. So if you have a previous assignment that you didn't submit, go in and submit it now. I reopened everything. That way I can actually look at it. And when you finish this one, you can submit it. What else? I am going through and grading your take home test at the moment. So if you see a really weird comment on your take home test, that's just my way of keeping track of things. And then I'm going to assign a grade based on that, based on how everyone does. So if you see like a weird strings of ones and zeros, don't worry about that so much. Any questions about the class or test or things coming up? No questions. Everyone's kind of good on that. Yeah, your test will be just on Google Classroom. Like pretty much everything we've done, it will. You can go in and you can work on Google Classroom, or if you need to, you can attach pictures. If you're just trying to do this over a phone or something, I understand how difficult it is to write things on the phone itself. So yeah. Is there a recommended time? So in general, I would recommend you try to spend 20 minutes per question or less. Just kind of how College Board does it. Um, so that would be requested. If I could, I would put a time limit on it, but I feel like that would be too restrictive for people just trying to get by on whatever technology they can use, or if they have to share computers or something. So this one, it is going to be 4 questions. So I would recommend you do it in maybe an hour to an hour and 20 minutes. And that would be probably where you'd be most prepared to do well on the AP test. But I can't really limit you time wise and feel comfortable about it. Anything else? But yeah, and otherwise, the test is probably just going to be curved. It's actually way more difficult trying to keep up with everything online with everyone's different types of technology situation. It's made grading much more troublesome. So yeah, your test is just going to be curved, and then once we finish the test, it's just going to be review, review, review continuously until the AP test. So the the comment on your take home test, it's just so it's my way of going through and scoring them before I assign a grade to it. I was intentionally not telling you which ones I was looking at in case people are still trying to get it turned in late. That way they can't go through and just only try to do that or only look at certain parts. And so, yeah, it will turn into a grade. I mean it. I guess in the in that sense, it kind of is a secret code because only I know what it actually means. But it's just my placeholder. So like I put the comment on each student, and I'll go through and put a grade after the fact. So yeah, it's not actually binary or something like that, if that's what you're wondering.
What's up with your profile picture?
Who was it? It was Andrew Wynn actually figured out the profile picture. They decoded it. It looks like a person eating. It's pretty simple. I mean, it can either be black or blue, so there's two possible values. So that should give you a hint how you could decipher it. The one that I'm actually waiting for people to figure out is what the thumbnail for each of the class videos is. That one I'm having more fun with. So I have like a Excel spreadsheet that converts it and then puts it into Mathematica and generates an image that actually has a message on every single one of those. From an early video game. No, I made it myself. Again, it was just through a simple like Excel spreadsheet and then put it through a math program that created an image. It's just me having fun, basically. All right, well, let's look at your warm-up. So we have a pendulum swinging, and it shows the motion there. Friction is negligible. Obviously, what's the first thing we should look at on this graph? ARG. Oh, boomer RPG list. I have thought about making an ARG, but a lot goes into that. So, yeah, we have a Y position versus time graph. We're trying to get kinetic energy versus time. How are we going to sketch kinetic energy versus time? So I do want you to sketch this out. So we have our Y position for the pendulum. We have our time. We have a negative sine wave. Something like this. Tier list of physicists. Maxwell is up there. Schrodinger. Einstein, I would actually put high up there, but below Maxwell. What tier would I be in? I would be an F rank. That's an easy one. Newton. I mean, I like Newton. Newton was really smart. Most people would put him in S rank. Definitely at least A. But mathematics gang. That would be not yeah, that was Galileo. So yeah, that would be Galileo. Galileo's up there. Probably A. Copernicus, I would put Copernicus kind of low. Like Copernicus, everyone like talks so much about him. I would put him at like a B. Because we had a bunch of data showing that the planet orbits weren't circular; they were elliptical. But he forced everything to be circular. He had some points, but yeah, I guess I could do that. I don't know who my favorite would be though. Just mad about Einstein. Einstein, he did a lot of things. He really combined a lot of things together. If you like read anything Einstein was talking about, he pretty much talks about how he was pretty sure Maxwell knew everything he was saying in the 1850s. So without Maxwell, there is no Einstein. Not saying that Einstein wasn't brilliant, didn't have like massive contribution, but I think Maxwell was more important to physics than Einstein was. So we need kinetic energy. Well, let's just look at that. 1/2 mass times speed squared. So we really need to be talking about speed. So what times are we moving the fastest?
I got the profile picture thing.
What does it say?
Physics.
Yeah, it just says physics.
Yay.
Yeah, it's physics and binary. The other pictures I was having more fun with. It's still relatively simple, but trickier. So we're trying to look at speed. What times are we moving the fastest then? So let's just look at our different times. We have 0 seconds, 1 second, 2 seconds, 3 seconds. What position are we moving fastest? Yeah, there we go. Why are we going fastest at 0, 2, and 4 seconds? So yeah, at our equilibrium position, we're going the fastest. Here, I don't have any spring potential energy at equilibrium, so all my energy is turned to kinetic energy. Or I could look at position time. The slope of a position time graph gives me velocity. Well, these are my steepest slopes on position times. So those are a few ways of looking at it. So I'm going the fastest through the equilibrium position. So what happens at my maximum displacement points? So 0, and I know it's hard to type a lot of text, but let's be really specific. What is 0? Our speed is 0. We stop at our endpoints. So I stop going backwards before I can go forward. I stop going forward before I can go backwards. Now, kinetic energy. What can I say about the value of kinetic energy, like positive, negative, things like that? Positive always. Mass can't be negative. Speed, I mean, we're talking with real speeds, no like complex numbers or anything. So speed squared is always going to be positive. Mass is positive. 1/2 is positive. So kinetic energy is always positive. So we always have a positive kinetic energy. So fast, 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 these are all going to be positive kinetic energies. So when I draw this, I have a big positive kinetic energy. I have a big positive kinetic energy. I have a big positive kinetic energy. And then here I'm stopped. So our kinetic energy is 0 joules. And so we can put this all together. Now it just says sketch, so I'm not caring so much about the values here. So we have kinetic energy in joules, time in seconds. 1, 2, 3, 4. So we start out here at equilibrium. We're going fast. So I have a big positive kinetic energy. So let's put a point here. 1, 2, 3, 4. At 1 second, we stop. So I have 0 joules of kinetic energy. 2 seconds, I'm moving fast again through my equilibrium position, and kinetic energy has to be positive. 3 seconds, we stop again, so we have no more kinetic energy at the extreme endpoint. And at 4 seconds, I'm back to going fast through equilibrium. It doesn't care I'm moving in the negative direction because I square the speed, so I get a positive number. And then how do I connect this? Is it going to be a sine wave or is it going to be a W? Yeah, sine wave. Well, and particularly a cosine wave that's been shifted up. But yeah, anytime we have simple harmonic motion, when we graph it, we're going to be seeing sines and cosines. And again, always positive or zero. I guess I should say always positive or zero, because you can't have zero kinetic energy. All right. Now we need to graph our spring potential energy. Not spring potential, or just, this is a pendulum. Why did I write spring? This should be gravitational potential energy for pendulum. Sorry, that was a typo right there. So gravitational potential energy, mass times acceleration of gravity times height. What can I say about gravitational potential energy? Can that be positive or negative, or is it always positive like the kinetic energy? So it's lowest equal. The gravitational potential energy, not so much. The spring potential energy would be, but here we have a pendulum. So yeah, again, that's a typo. On your warm up, change that spring potential energy to gravitational potential energy. So yeah, if we have zero height at so we can define this in a few ways. I could put my zero height here and then make my gravitational potential energy never negative. But if we use kind of the convention the graph used, we could have a positive height or a negative. So if we use this, then we could be positive or negative. So our gravitational potential energy could be positive or negative, depending on where we put our zero. I'm just going to go with the zero that was set up there for us already. So then let's look at our time. 0 second, 1 second, 2 second, 3 seconds, and 4 seconds. So I'm just going to call this zero height because this is what our graph is showing here. So this is height is 0 meters. So it's 0 seconds. If we use the convention of this, my height is 0 meters. So my gravitational potential energy is zero. So I have 0 joules of gravitational potential energy. You did not miss any kinematics, no. At 1 second, our height is below where we called our 0, so we would say negative height. So our gravitational potential energy is negative, and we'll see a big negative. Because this is the lowest we go. Kinematic equation tier list. Yeah, I don't know which ones I would rank. Probably second, third, first. In the order from best to not as good. Yeah, second is definitely one of the more useful ones. The first is kind of the least useful, even though it's the easiest to use. So what's happening at 2 seconds? The fourth kinematic equation is also useful. It's just dealing with average speed. I mean, you can get a lot of kinematic equations. Technically, every time we derive anything using the kinematic equations, we're getting our own kinematic equations. So at 2 seconds, what's going on with our potential energy? All right, so 0 joules. So we have a height of 0 meters. So I have 0 joules gravitational potential energy. I just realized something. Yeah, we also need to change this graph. What am I doing here? This needs to be an X position. Yeah, we actually really need to change this. So let's look at this. So we have a pendulum that's going back and forth like this. Yeah, otherwise we're about to mess something up. So yeah, this needs to be my X position. So this would be my negative X position, my equilibrium, and my positive X position. So that actually can't be my Y value. So yeah, I really should have. It looks like when I made this, I was mixing up springs and yeah, so now we're going to put 0 height at equilibrium. Yeah, you are right. We do need to change this up. Sorry about that. That's my bad. So yeah, so our equilibrium is going to be the 0 height still. So we do have 0 height here. So we are still correct at any time we're going through our equilibrium position. We are going to have 0 joules, but this is going to change it up. So if I'm at negative X, what's my height right here? Yeah, so that would have to be positive. Yeah, sorry about that. It has been a long week. So yeah, so we are still at a positive height right here, and then we get to this side and we are at a positive height again, and we would have 0 height at our equilibrium. Sorry, Daniel, you were correct the whole time. All right, so then yeah, we are at equilibrium, so we're at 0 height. Then we go to the negative X position, so we're at a positive height. We go back to equilibrium, but then we go to our positive X position, which is also at a positive height, which means we have gravitational potential energy is going to be a big positive value, but we go from our positive displacement back down to our equilibrium position, so we end up back at a height of 0 meters. So we end up with 0 joules of gravitational potential energy. Yeah, that was my bad. So now we'll graph this, put this all together. How we did this by putting our lowest point at 0. We're not going to go below 0 for gravitational potential energy versus time. So we start off with 0 joules of gravitational potential energy. 1, 2, 3, 4. At 1 second, I have a big positive potential energy. 2 seconds, I have 0 at equilibrium gravitational potential energy. Then at 3 seconds, I have a big positive value again. I'm at my highest point again. And then at 4 seconds, I'm back down to my equilibrium position at 0. Just like kinetic energy, just like our graph, everything we see here is going to be some sort of sine wave. And these should match up. I'm going to have maximum kinetic energy when I have 0 potential energy, 0 kinetic energy when I have maximum potential energy. maximum kinetic energy when I have zero potential energy, zero kinetic energy when I have maximum potential energy, and maximum kinetic energy when I have zero potential energy. So then what's our total mechanical energy graph going to look like? If we just kind of have reverses of these, friction is negligible. This is the easy one to draw. Yeah, no friction. So I have a constant positive total mechanical energy. On your picture, let's make sure we draw our time axis. If I just have a graph and I draw it like this, which one of these is my axis and which one is the graph? We don't know whatsoever. So let's make sure we at least graph our time axis so it's obvious this is our total mechanical energy. Yeah. You can tell because that's not always how people draw, though. All right, questions on that, even though I kept confusing myself. Sorry about that. So TME is what? What? Oh, I'll let you retract that joke. Let's not make jokes about that. All right. So now we're going to sketch our energy versus position. Made kinematics the universal language. Would you have to describe all letters in terms of kinematics? Give an equation to trace your pencil? Because you could do that. It would be, what is it, like vector tracing, I think is what it's called. Old video games used it. But yeah, you could describe all the motion by a vector. All right. So now we want energy versus position. So kinetic energy versus position. Now I really only have three positions to look at, right? My negative maximum displacement, equilibrium, and positive maximum displacement. So not position, not velocity, but position. that's pretty much all of physics. The entirety of my physics career was thinking this class is really hard, and then I go on to the next class and I was like, that class was really easy. Like every single time without fail, I would like struggle through the class, and I would look back at the math and I was like, why did I struggle with that? But that's just life. So we have positive x, 0, and negative x position. So at my positive x, when I'm furthest from equilibrium, big or a small kinetic energy? So on my map, my maximum displacement am I going fast or slow? Slow. And in fact, you stop completely. So yeah, that's our slowest point. So at our maximum displacements, we stop. So our kinetic energy is 0 joules. Kinetic energy is 0 joules. Now, 0, this is our equilibrium. So we're going equilibrium. What can we say about our speed at equilibrium? So maximum speed. So we're going fast. And if we're going fast, then we have a big kinetic energy. And then kinetic energy, again, always going to be positive, at least for everything we do. I mean, you could come up with a math question where you could have a negative kinetic energy, but we're always dealing with positive kinetic energies. 1/2 mass always positive, speed squared always positive. Big kinetic energy there. So we can graph this out. Let's put our axis in the middle here now. So we have our kinetic energy versus position. So we're at negative x, 0, positive x. So positive and negative x, I have no kinetic energy. At equilibrium, I have a lot of kinetic energy. And just like everything before, we're connecting this with a curve. I mean, just pretty much everything about pendulums and simple harmonic motions should be making you think this is probably going to be a curve. So then we can look at our gravitational potential energy. So at our maximum displacement, at equilibrium, at our negative displacement. So which of these do we have a positive height at? How do we know if the curve is up or down? Well, we could, what's the best way of, I mean, yeah, probably the best way of thinking of it. So versus time, so you can think of right here, when we're far away, we have a big spring force, or not a big spring force, but we have a big restoring force. The further and further I pull the pendulum, the more and more force I have pulling it back to the center. So further from equilibrium, I have a bigger force, bigger acceleration. So I'm gaining speed faster. So I'm gaining kinetic energy faster here. Between these 2 points, the difference between here and here, we're getting small forces. So if I have a small force in this region, I have a small acceleration. My speed is changing at a slow rate. So my kinetic energy is changing at a slow rate here. At equilibrium, it is at constant speed, so change in kinetic energy is a better way of at equilibrium, it's constant speed. So the change in kinetic energy is actually 0 at that exact moment in time. If that's where you're getting at, but yeah, you have that's why you end up having to have a slope right here. And then the alternative is it would be really weird to try to connect like that. You would be saying you're getting energy fast, and then yeah, you don't see many shapes like that in the real world. All right, so positive x, we're at maximum height, maximum positive height, but also at negative x, we're also at the maximum positive height. Right, at our endpoints, we're at the highest point, but in the equilibrium, we're at the lowest point. So maximum positive height, which means we have the maximum positive gravitational potential energy at our endpoints. But at our equilibrium, we have no gravitational potential energy. So I can combine this all together. So at my negative x and positive x, I have maximum potential energy. And at my equilibrium, I have no potential energy. And again, we can see it's a parabola. Again, back to this. When I'm far from equilibrium, the pendulum is going to accelerate down rapidly. So I'm going to be losing height really rapidly here. But when I get lower, I'm not losing height as rapidly between this point. And I can't really, that'd be kind of a trig argument you would have to make. But just think about right here, you're falling a large distance per angle, but here you're falling a small distance per angle. So a small change in height per change in angle. I don't want to have to make a trig argument for that. I think it's a little bit better if you can just see it. Was everyone able to kind of see that? I mean, yeah, it's pretty much a position. Yeah, there we go. That's a really good way of putting it. It's pretty much a position graph because this is mass times acceleration due to gravity times height. So yeah, we're not changing mass. We're not changing acceleration due to gravity. So yeah, we're just looking at height. So it should just look like pendulum. And then C total mechanical energy, no friction. We see that kinetic energy is 0 and potential energy is maximum. Potential energy is 0 and kinetic energy is maximum. Potential energy maximum when kinetic energy is 0. So this should be another real straight one, positive x, negative x, 0. About the only thing to really watch out for is you do have endpoints. Our graph does not go beyond these endpoints. So if you were to just draw this graph out as far as you want, you would actually lose some points. I don't know how this like religion of kinematics started. And then the question, how would the graphs change for a spring? We've kind of spent a lot of time on this. Our spring graphs are going to look pretty much the same. Galileo Galilei. You know, Galileo made the most powerful telescopes of his time, and I forget what Italian city he lived in, but it was like a Italian city by the coast, and the government thought it was so important to have him there because if you had optical devices, you could see warships off in the distance. And so he was pretty much under continuous house arrest because the government thought he was too critical to let him go anywhere. And he was pretty much forced to continue making better and better telescopes for the military. Just a random thing. And then yeah, there's one last thing on the very bottom. Yeah, that's why you don't make yourself too important, or the government won't let you go anywhere. So I don't know. I like don't really know when that came up. I mean, in all honesty, a large portion of science wasn't done in a vacuum. A lot of it was um, was funded by the military or by the government. It's kind of like the Hubble telescope, how it was like a close to $1 billion satellite, but they were pretty much it's identical to spy satellites that the government was putting up. So they have something like 12 identical satellites to the Hubble telescope that the U.S. government has just pointed down towards the Earth to spy on people. And then they just gave us the one that we could look out into space. So just all these random things that are like funded by the government. If instead of spying on people, we just turned all 12 of them out and looked into space, that would be pretty cool what we could actually see. All right, so we have this here. So yeah, just kind of a few things that we can do with this. We haven't really used this equation a whole lot. So we have the A is our amplitude. X is going to be our current position. And then obviously frequency and time, or angular frequency. So just kind of something that you could see come up on the test is they give you an equation like position equals 2 times cosine times, let's just say pi times time or something like this. So let's say we're given this equation. X equals 2 cosine pi times time. What are some things that I could get from this equation? I could get A. What is A? What's our amplitude? Oh, wait, it didn't keep. Why did this stop scrolling? Yeah, so that's amplitude. So yeah, so we could get things like our amplitude is equal to 2. I mean, this might be meters, so it might be 2 meters. So we could get our amplitude from this. Well, we know that this is angular frequency times time, so I can know my angular frequency, otherwise known as angular speed, would be pi. But we also have on our formula chart that it actually has it written 1 over frequency is angular frequency. No, it's not. It's 2 pi divided by angular frequency. That's how it's written. How you'll see this written a lot of times is I can multiply angular frequency over and frequency over. So I can get angular frequency as 2 pi times the frequency. So I could get amplitude as 2, and I can figure out what my frequency is from this. So my angular frequency is pi. So pi is equal to 2 pi times the frequency. And so some people already beat me to this. So I can divide 2 pi over, and I can see my frequency is 1/2, right? Pi divided by pi goes to 1. Then I divide the 2 over. So just something they could give us. So I could have like 1/2 hertz for my frequency, or pi radians per second for my angular speed. Another thing they could do is if they give us that equation, they could say like let's rewrite that and pretend I didn't just forget how to spell what for a second. What is the position at, say, 2 seconds? Actually, let's make this a little bit. Let's say at 3 seconds. So if you get what is the position at 3 seconds? So I could go in and try to figure out what my position is. So position would be 2 is my amplitude. So I'm going to be oscillating back between -2 and +2, right? Just like here, I was going between -5 and +5. I'm going between -2 and +2. I can substitute this in. Cosine of 3 pi times time. What do I do? Pi times 3 What's cosine of 3 pi? What's cosine of 1 pi? So that would be cosine of 3 pi is -1. So -1 times 2. So I would get my position would be -2. So at 3 seconds, I could say I'm at my negative amplitude. Or I could say, I could try to get position at, say, something a little bit different, like 1.5 seconds. So we can put that in. So my position, where I would be, is 2 times cosine of 1.5 pi. And by the way, what mode should our calculator be in here? Yeah, this is definitely, see this 2 pi? This whole equation needs to be in radian mode. So yeah, that is the one time this year that we really need to be sure you're in radian mode. So we would do this. Cosine of 1.5 pi is zero. So here we could see at 1.5 seconds we're at equilibrium, or I could do position at, say, like 0.25 seconds. And then we would have to do position would be 2 times cosine 0.25 pi. And then, yeah, we would be at 1.414 at that moment. So that's what that equation is pretty much giving us. So if you're ever given that equation, they could either be giving you this equation and asking you where you are at that point, or they could give you this equation and ask, what's our amplitude? Or they could give us an equation and ask us, what's the frequency of the motion? Or if they ask for frequency, they could ask, what's our angular frequency, angular speed? Or they could ask for period, right? Period is 1 over frequency. So just random things they can do with that equation, even if it doesn't show up a whole lot, it's still a possibility. All right, any last minute questions? Now that we spent 50 minutes on the warm up? Not that we've ever done that before. Thirty, 35 to 40 minutes. I mean, there's random distractions in there. But yeah, we started recording at like 10:10, and now it's 10:58. Unless I'm hallucinating. All right. Yeah, if we ever spent most of the class on something, it was intended to be that way. Like I intentionally made it really long and I had a lot of points to hit, and it just kind of turns into the lesson halfway through class. Uh, so it's usually not by the warm up. I just like gradually transition away from the warm up or into other questions. All right, so now we have a few questions I'd like to work on here. Just 2 more questions with springs that I thought we should cover before the test. Yeah. All right, so again, for these 2 questions, still work through them. You don't need to actually write the question for them unless it's helpful to you to prepare for the test. Just write the answer, go work through it, take a picture, post on Google Classroom, get a free 100. So as shown above, you have a mass m sliding on a horizontal frictionless air track with a speed v. When it instantaneously hits and sticks with a 3m mass initially at rest on the track. So that instantaneously just means the collision is perfect. Right when they collide, they stick together. So no like wiggling, no real world effects. So ignore all that. The 3m mass is connected to one end of a massless spring, so the mass is not going to affect the momentum, which has spring constant k. The other end of the spring is fixed. So A wants us to determine the following for the mass immediately before impact. So this should be relatively straightforward. Momentum and kinetic energy. This question here, by the way, was stolen from a College Board. It was a Physics B question, so not a Physics 1, but still an AP style question. Linear momentum. Well, that's easy. Momentum is mass times velocity. We have a mass m and a velocity v to the right, so I'm going to call that positive v. So my momentum is positive mass times velocity. Don't you wish all questions were that easy? Two wants us to get the kinetic energy before the collision. Well, kinetic energy is 1/2 mass times speed squared. Mass m, speed v, squared. All right, B. Now the masses collide, and they want us to get the values immediately after impact. Why are they stressing the word immediately right there? Yeah, it's dealing with the spring. So if this is right after the collision, what has the spring not had time to do yet? Yeah, so the spring has not been allowed to compress yet. So that's why they're saying right after the collision. So the collision has happened, but the spring hasn't compressed. We're not dealing with any spring potential energy or anything like that. So what's going to be my total momentum after the collision before the spring compresses? Yeah, it's still just positive mv. Now, this is not going to stay this way. Well, yeah, we'll get the speed in just a second, yeah. But yeah, the momentum has not changed yet. The momentum will start to change as the spring gets compressed. It's going to be losing speed, and so momentum is going to be lost from the two blocks. And in turn, the momentum is just being put into the earth itself. But right after the collision, we haven't had time to lose momentum yet. And Connor's on the right track here. For 2, we're trying to get kinetic energy after the collision. but we have an inelastic collision, which means, wait, that just says 1L. So that means we lose kinetic energy. So we are going to have to find the speed. So we know our total momentum before the collision equals total momentum after the collision. So we started out with mv, momentum before the collision. After the masses collide, they stick together and make one block with mass m and 3m combined together and move with the same final speed. So mv equals 4 mass times final speed. You divide out your mass, you divide it by 4. So we see the final speed of these two blocks is 1/4 the initial speed of that first block. And if you're really lazy, you can get this all by ratios. I went from mass m to 4m, so I ended up with 4 times the mass. So I have 1/4 the speed. So now that I know speed, now I can find my kinetic energy final. So my final kinetic energy is 1/2 mass times that final speed squared. What's my mass? Yeah, it's going to be both masses stuck together, so mass m plus mass 3m stuck together, times 1/4 v squared. Again, let's make sure to put the 1/4 inside of the square. So I have 1/2 times 4m. 1/4 squared is 1. I'm just going to leave that as 1/4 squared. V squared. So 4 divided by 4 squared is just 1/4. 1/2 times 1/4. One half of 1/4. 1/8 mass times final speed squared. So yeah, we definitely lost some kinetic energy. We end up with 1/4 of the kinetic energy. And this isn't final. What am I saying here? This is just V, because this is the same as my initial speed I got by solving from here. So we lost 3/4 of our kinetic energy. The 1/4 squared, yeah, 1/4 squared, but then I had times 4. So 4 divided by 4 squared is 1/4. Can I B1? Well, B1, so this is right after the collision, before the spring has compressed. So because the spring hasn't compressed yet, because it says immediately after the impact, that means our momentum after the collision is exactly going to equal the momentum before the collision. Once the spring begins to compress, the blocks are going to lose momentum. Does that make sense, or is it still confusing? Because I would say, yeah, BI is more conceptual than actually having to do any math. All right, now we have after the collision, the two masses undergo simple harmonic motion about their position at impact. So that's their equilibrium position where they collided. So C wants us to determine the amplitude of the harmonic motion. Any guesses on how to start that? All right, so we have kinetic energy. Now, this is kinetic energy right after the collision that we have here is turning into spring potential energy. Now, we could try using the amplitude is equal to, or the position is amplitude times cosine of the angle. Or cosine 2 pi times frequency times time. We just don't know enough information about that. Like, what's our time? What's our frequency? What's our amplitude? We could get our position. We start at a position of 0. But yeah, there's a lot we don't know about that equation I just introduced. So yeah, we're kind of stuck using this. And so if we're trying to find amplitude, the other way of saying amplitude is just saying the maximum displacement. So this is where we're going to use conservation of energy. So we start off with all kinetic energy, the kinetic energy after the collision. All gets turned into spring potential energy. And we're going to stop at our maximum displacement. So that means our kinetic energy is 0 here. So we start off not compressed, spring, and then we end up here, we stop at that maximum displacement. All right, so we already know our kinetic energy is at 1/8 mass times the initial speed squared. This is all turning into spring potential energy, 1/2 spring constant times that distance from equilibrium squared. All right, so we do know values. They did give us spring constant K. We do know mass M. We are given speed V. So we really just have to substitute values over. 1/8 times 2. 1/4. I have a mass. I'm dividing spring constant over. Mass divided by spring constant is equal to that position squared. And this is going to be our maximum displacement position. So I could have also written that as amplitude squared. And I lost my v squared. I accidentally dropped a v squared there. And then I can take the square root of both sides. So my amplitude is going to equal the square root mass times speed squared divided by 4 times the spring constant. And we can pull some things out of the square root, like square root of speed squared is speed, square root of 4 is 2. But I still need to leave mass and spring constant inside the square root. And then we do have plus minus, but this is asking for amplitude. So which solution are we taking, the positive or the negative? Yeah, we are taking the positive. So yeah, that is a good point. We did get plus minus whenever we did this. But for physics, we're going to choose the answer that makes sense. So we're going to choose the positive answer because amplitude is always positive. But yeah, it's definitely a thing to think of, especially when you use your beloved kinematics. And then D is kind of easy because period, we just need to use our spring period equation. Period of a spring is 2 pi square root mass divided by a spring constant. And which mass are we talking about here? Mass M, mass 3m, or both masses? Yeah, it's going to be 4m because the masses are combined together, so that total mass is going back and forth between two sides. So 2 pi times the square root. Our total mass now is 4m divided by our spring constant. I could pull a 4 out of the square root. 2 times 2 pi square root of mass over spring constant. So the period of the spring is going to be 4 pi times the square root mass m divided by spring constant k. And then now that we know all this, now that I know my period and I know my amplitude, now I could build that equation like we did in our warm-up. So I would put this in for the a value period. I would do 1 divided by this and then put that in as my frequency. Multiply it by 2 pi, multiply it by time. Questions on that one? And again, this was a college board question. It had numbers, so I changed it up to not have numbers. But this is about the level of difficulty of math that I really expect from an AP style question. Like, I don't think we did any crazy difficult math, but there were plenty of places that you can mess up. So if there's no questions on that, then just have one more I want to look at. So I like this question. We have two masses connected by a spring as shown below. Both masses experience an equal acceleration. So A wants us to find the spring force acting on that mass 3m. How should we start this? All right, so spring force. So spring force is equal to spring constant times position. Spring force is equal to spring constant times that displacement from equilibrium. What do we know here, though? Do we know the spring force? Do we know spring constant? Or distance from equilibrium? So probably not using that. So we do know force F, but that's the spring, that's the applied force to both. So we do know F equals ma, so I could do net force is equal to mass times acceleration. Both masses have the same acceleration. All right, so what's my net force? So F, what's the mass? Yeah, F is applied to both masses, 4m times acceleration. So I know F, I know m, I could divide 4m over. So I get force divided by 4 mass is equal to our acceleration. What now? So this is our full system. Are we trying to find the spring force on both objects or on one object? We're trying to find spring force on one object, so this is only on 3M. So using acceleration. All right, so net force is equal to mass times acceleration. What forces are acting on mass 3m? Let's draw a free body diagram for mass 3m. All right. Using spring potential energy. Yeah, spring potential energy has the same drawbacks of this because it's the same two variables. So if I could use spring potential energy, I should also be able to use spring force. Unless we know a little bit more about force and distance. All right, so I have spring force pulling it this way. I still have normal force and weight. Now, what do they mean by air track? Yeah, no friction. This is like an air hockey table. If anyone's ever seen an air hockey table, it means very low friction. Very low friction, which pretty much means we're going to say no friction. So air track is pretty much saying no friction. So this is our whole free body diagram. These two things balance out. So what's my net force equal to? Yeah, my normal force and weight balance out, no friction, so my net force is the spring force. Well, I know net force is mass times acceleration. So my spring force is equal to, I'm looking at mass 3m. And I know my acceleration from here times force divided by 4m. M divided by m divides out. Spring force would be 3/4 the force applied. And probably the biggest thing here is that they both have the same acceleration, which means that the spring isn't sitting there bouncing back and forth like this. We've kind of reached an equilibrium position with the springs. And then if we were kind of really lazy, since they have the same acceleration, well, I have m and 3m. So I have 4m to play with. Well, this is going to take up 3/4 of it. And then the other mass m is only going to take 1/4 of the force. Or you could do the math and prove it. So we ended up not even needing this equation because we had so many unknowns there. All right, now I can get B. B wants to know how far is the spring stretched from equilibrium. How can I do that? Yeah, now we can use our spring force equation. Now we know what our spring force is spring constant times distance from equilibrium. All right, so I know my spring force, 3/4 F. What's our spring constant? Is it? Or does it say K? Does it? Give me a second here. Forgot the exact thing I was trying to ask in this question. Yeah. So I did intend to give you spring constant. Yeah, so we do know spring constant K. Sorry about that. Yeah, there is a little K. It wasn't so much did I put it in the question. It was that on accident or not. So there's a reason I was trying to remember if I intended to give that to you or not. So yeah, we do know our spring constant K times how far this thing is stretched from equilibrium. We'll just leave that as X. And then I can just divide spring constant over. So 3 times force divided by 4 times spring constant is equal to position. Yeah, sorry about this. I put this together yesterday and I couldn't remember if I intended to put spring constant in there or not. And then I was blanking on whether or not I did. All right. How do you solve it if I didn't give it to you? Yeah, that would be you would need I guess you can't. I was trying to think. Sometimes I work these out beforehand and I know and there's certain ways to get a second equation. And I was trying to remember if this was the one where you needed a second equation. But yeah, it doesn't look like you can unless someone sees something I'm not doing. I'm not seeing. All right. Now C, now the situation is what happens if we use spring force of the small mass? The problem is the spring isn't dragging the mass M along. So the spring is an internal force. So that force is going to be the same on both masses, right? Due to Newton's third law. As long as the spring isn't oscillating back and forth anymore. So here it's a constant acceleration, which is implying both have the same acceleration. So if they have the same acceleration, they can't be bouncing like this, right? If they're bouncing like this, then they don't have the same acceleration. So because the spring is not bouncing, that means we're in an equilibrium state, which means that this spring is going to pull on mass 3m with an equal force in the opposite direction that the spring is going to pull on this one. So if we decided to use the force on the smaller mass m, it's still going to be the same 3/4 F force due to Newton's third law. The only time it would be something different would be if the system's not in equilibrium. So the spring does stretch. It's not that the spring doesn't stretch. It's just that it's stretched by a constant amount. So let's say it's stretched this much from equilibrium, but it's staying that much. Because if it was changing how much it was stretched by, these two masses would not have the same acceleration. So by saying the masses have the same acceleration, implies that the spring itself is stretched. There is a force, there is an acceleration, so the spring is stretched, but it's stretched by a constant amount throughout the entirety of the problem. So it's not that the spring doesn't stretch, it's that the spring is stretched by a constant amount. Is that clear or no? Because that's probably the most difficult conceptual thing about the question, is getting from the point both masses have equal acceleration to realizing that means that the spring is stretched by a constant amount at all points. So if you're having confusion there, you found the right spot to have confusion. So it stretches, it didn't necessarily stretch instantaneously. So if we're accelerating it, this part would probably accelerate faster initially, and then this would like catch up, and then this back part would oscillate back and forth. But over time, the oscillation will kind of damp down. I guess, yeah, since there's no friction, it's usually friction that does that. I guess if in this like imaginary question without friction, yeah, it would just be stretch instantaneously. Or someone went and like got it to stop oscillating. But yeah, it's been accelerated for long enough that it's kind of caught up, and it's just in a stable state where it's stretched by a constant amount. All right, so C, we're changing which side we're pulling on. Now I'm putting my force on this side right here, attached to the 3m mass. We still have our spring here, mass m. Again, same situation where we have a constant acceleration. So not, yeah, both masses have the same acceleration is what I meant to say, but it is also constant acceleration. So 1, how will this change the acceleration of the system of masses? So what's my acceleration of the system of masses? Well, net force equals mass. I'm looking at my system. Yeah, so total times acceleration. So my force F is equal to my total mass is 4m times acceleration. So yeah, my acceleration is still force F divided by 4m. So no change. So my acceleration stays the same. I have an identical force and an identical total mass of the system. All right, so now 2 wants me to figure out the spring force acting on mass m now. Is this going to be the same or different? Yeah, this one is going to be different than before. So we're going to go back to the same thing we were doing up here. I know the net force is just the spring force, right? The only thing pulling this mass is spring force. Normal force and weight cancel out, and we don't have friction. It's pretty much the exact same free body diagram as this, except the other direction. So for mass m, now we have a spring force this way, and normal force and weight balance each other out on the flat surface, mass m. And then this is all equal to mass times acceleration. So we have our spring force is, yeah, that's what we're looking for. What am I saying? Spring force is equal to the mass. Now we just have mass lowercase m, right? I'm only looking at this mass right now, not the total mass. But I'm trying to find the spring force acting on mass m, so only that one mass. And then I have my acceleration, force divided by 4m. So spring force, m divided by m. I have 1/4 the force. Which again kind of makes sense. I need a bigger force to accelerate the 3m mass than I do to accelerate the m mass. And if we look here, 3/4 and 1/4, so 3/4 of the force is going to the 3m mass, 1/4 of the force is going to the 1m mass, as long as everything's accelerating at the same rate. Because I have 4m to accelerate, 3m is hard to accelerate, so it's going to take 3 out of the 4 available. M is easier, it's only 1m, so it's going to take 1 out of the 4 available. And then 3, does the spring stretch more or less than it did before? Yeah, why less? Yeah, spring forces, spring constant times displacement. So yeah, like you said, we have a smaller force, or force went down, but we have the same spring constant, which means that amount the spring is stretched is going to be less. So that's the mathematical way. So I have a smaller spring force, didn't change the spring constant, so the spring is stretched less. Or we can just think in the obvious way. When I'm pulling a smaller mass, the spring is going to stretch less than the first one where I'm pulling the entire mass 3m. So there were some few tricky concepts, even if the math wasn't difficult anywhere. Again, probably the most difficult thing is equal acceleration for both masses means that that spring is not bouncing back and forth at all. The masses have to be moving at the same rate. That was kind of their way of saying the spring was at a system equilibrium position where it wasn't bouncing around and changing. Questions on this one? So this was all I really had planned today, and that was good. We've been recording for about an hour and a half. So questions on 1 or 2 or anything that you didn't see? Again, take a picture of your warm-up, post that on Google Classroom, take a picture of the homework, post on Google Classroom. This would be identical. Oh, not identical, but yeah, it would be very similar if it was a string. The only thing is we normally deal with non-stretchable strings, and so yeah, it would be a similar thing where we'd be talking about tension, where this tension would be less than the first question. When 3m is getting pulled, it would have a bigger tension. But yeah, everything would be identical. We just wouldn't be solving for the amount that the string itself was stretching normally. But yeah, very, very similar question. So what about on number 1 are you asking about? You just want me to like put it back up here so you can look at it, or was there a certain thing? Wait, no, this was a warm up. Wait, which one was it on? I put it somewhere. But yeah, this was it. So yeah, again, take a picture of the classwork and the warm-up. The warm-up, I do want you to write the question. Classwork, you don't have to. Make sure you're studying. Test next Tuesday. I will log into Google Classroom and I will do maybe like 15 minutes of me working through something that might be confusing to you. So I definitely would suggest you come look at the stream that I post. That would be helpful. The thumbnail pictures, very similar to the binary you just did. Most of them are kind of boring, but I've started having some fun with them. So similar to binary, but not binary. So if there's no more questions, just make sure you're studying for the test next Tuesday. And then after that, we're going to have a lot of review, and just everyone have a good day. I'll stick around for a little bit longer if you still have some questions, but we're going to stop recording now.